Hey everyone, and welcome back to the channel. Today, we're tackling LeetCode problem number 23, Merge K-Sorted Lists. This is a classic problem, often seen in coding interviews, and it falls under the dynamic programming category, though we'll see a clever approach. The problem statement is simple. You're given an array of K-linked lists, each sorted in ascending order. Your task is to merge all these lists into one single sorted list. Think of it like merging multiple already sorted decks of cards into one perfectly sorted deck. Seems simple, right? But the elegance lies in finding an efficient solution. We'll explore different approaches, from a brute force method to an optimal solution, and I'll walk you through the Python code step by step. So, are you ready to dive into the world of linked lists and conquer this challenge? Let's get started. Understanding with examples. Let's clarify with some examples. Imagine we have three sorted linked lists. The first one is 1, 4, 5. The second is 1, 3, 4. And the third is 2, 6. Our goal is to merge these into a single sorted list. Think about it intuitively. You'd start by comparing the smallest elements from each list, 1, 1, and 2. We pick the smallest, which is 1. Then we move on to the next smallest elements in the lists that still have items. Then we'd compare 4, 3, and 2, choosing 2. After that, we compare 4, 3, and 6. We continue this process until all lists are empty. The final result would be 1, 1, 2, 3, 4, 4, 5, 6. See how we systematically picked the smallest elements at each step? Now that we have a better understanding, let's consider some approaches to solve this systematically. Brute force approach. One way to solve this is the brute force approach. We could concatenate all the lists into one big unsorted list and then sort that list using a sorting algorithm, like merge sort. While this works, it's not efficient. If each list has n elements and we have k lists, the concatenation takes O of k times n time. Then, sorting this entire list would take O of k times n log k times n. This becomes quite slow as k and n increase. We're basically throwing away the initial sorted nature of the individual lists. So, while simple, this approach is not ideal for large inputs. Let's explore a more optimal way to take advantage of the fact that our input lists are already sorted. Optimal solution. The optimal solution uses a priority queue, or a min-heap. We'll add the first node from each list to the priority queue. The priority queue will always give us the smallest node across all lists. We take that smallest node, add it to our merged list, and then add the next node from the list that the smallest node came from. This process repeats until the priority queue is empty. Using a min-heap, finding the smallest element is O of 1, and insertion and deletion take O of log k. This significantly improves efficiency. This method smartly leverages the pre-sorted nature of the input lists and avoids unnecessary comparisons. Code implementation. Let's see the code in Python. We'll use the heap queue module for the min-heap. First, we create a min-heap containing tuples of node value, list index, and node pointer. We iterate until the heap is empty, always extracting the smallest node, adding it to the result, and pushing the next node from its corresponding list. We'll handle edge cases carefully like empty lists. Code implementation shown visually and narrated step by step. This approach is much more efficient than the brute force method, utilizing the pre-sorted data structures in a smart way. Don't forget to handle the edge cases. Time and space complexity. Now, let's analyze the time and space complexity. Because we're using a min-heap, the time complexity is O of n log k, where n is the total number of nodes across all lists, and k is the number of lists. This is because inserting and extracting from the heap takes O of log k time. The space complexity is O of k, because we need to store k pointers in the priority queue. The space to store the result is O of n. Therefore, compared to the brute force approach, this method is significantly more efficient, especially when dealing with a large number of lists. Engagement break. Before we wrap up, I hope you found this explanation helpful. If you did, please give this video a big thumbs up. Also, don't forget to subscribe to the channel for more LeetCode solutions and algorithm tutorials. And let me know in the comments what other LeetCode problems you'd like me to cover next. Your support means a lot. Conclusion. So, we've successfully tackled the merge k sorted lists problem. We explored a brute force approach and then implemented